In this video, I have taken up another problem, which is of finding Thevenin's equivalent and Norton's equivalent for the same network. I've done few videos on Thevenin's equivalent, but I have not done any problem on Norton's equivalent. So I thought, let me take up this example wherein we will try to find out the Thevenin's as well as Norton's equivalent for this given network. We know that the Thevenin's equivalent of any network between a pair of terminals is a simple practical voltage source. It is as simple as that. Whereas what is a Norton's equivalent? Norton's equivalent is the current source equivalent of any given network between a pair of terminals. Or in other words, we can say that the Norton's equivalent is a dual of Thevenin's equivalent. We can claim to say so. So how does a Thevenin's equivalent appear like? A Thevenin's equivalent network of this particular example of this problem would be like a voltage source. For that matter, for any network, this is how the structure is going to be. This is a voltage source equivalent. That's what we call as Thevenin's equivalent. Thevenin's equivalent. This Thevenin's equivalent has got a voltage source whose magnitude is nothing but the open circuit voltage between the pair of terminals under consideration. And this is what we call as the Thevenin's resistance or impedance in general. So this is between A and B. So what we mean to say is the network that is linear in bilateral nature, this network between this pair of terminals A and B can be replaced by a voltage source. It is as simple as that. If we can replace this entire network by a current source, then we call that as a Norton's equivalent. We'll talk about that later. But then we will try to do the Thevenin's equivalent first. Alright? Or else I'll give the Norton's equivalent also. How does a Norton's equivalent appear? Norton's equivalent would be like this. You will find out the Norton's equivalent to be of this nature. We will have a current source. Current source, as we know, has got a resistance or impedance in parallel. This is the Norton's resistance, and here this is the Norton's current source. Now this is the current source equivalent. This is Norton's equivalent. Okay, between the same pair of terminals A and B. So in Norton's equivalent, we try to find out the Norton's current, which is nothing but the short circuit current between the pair of terminals. So we need to find out three things. One is this open circuit voltage between A and B of this network, short circuit current between A and B of this network. Then we need to find out this Thevenin's resistance, which is same as Norton's resistance. These are the three steps that are involved. Okay, so we will try to go ahead with each step. And we will try to find out the Thevenin's equivalent and Norton's equivalent. So, however, before starting any problem, it is always preferable to look at the problem little carefully. So, what are the things that are there in the network? What is it we are supposed to find, etc., etc. If we look at this network, we can see one voltage source, which is an independent source. And we have got resistances, of course, and there is another source here. This we know by nature is a dependent source, because of its representation. This has got a rhombus representation, and there is an arrowhead within it which says that it is a current source. This is a dependent current source, right? So when we say it is a dependent source, so the magnitude of this source has to be dependent on something else. What is it that decides the magnitude of this current source? It is the current through 8 ohm resistance which decides the magnitude of this current source, this dependent source. Or in other words, this current source is a current dependent current source. So we need to understand this much, right? So otherwise we will proceed with the different steps that are involved in finding out the Thevenin's equivalent and Norton's equivalent. Let us try to write the step 1. I will try to put the step 1. Okay, let me use a color. It picked up to black or what? I'll try to take this yellow color. I don't know why it changes to black without any. Let me not bother. Let me write only. I thought I would take up the text box. Anyway, it's not working fine. Let me not bother much. I'll pick up a color pencil. Then I will write step number 1. What is the first step that is involved? The first step that is involved is to calculate, to find VTH, the Thevenin's equivalent voltage. Okay, what is the Thevenin's equivalent voltage? It is same as the open circuit voltage between the pair of terminals, right? So in order to find out that, I'll try to reproduce this network. I'll take this network. Okay, I'll copy this network, bring it down here. Okay, I will try to find out the open circuit voltage. Okay, so the open circuit voltage that I'm trying to find is this. VTH is VOC. So what is the voltage that would appear between A and B? Right, so we need to find out this voltage. So you have different methods of finding. You can find out VTH by any method. Simple KCL, KVL will give us the information about VTH. Suppose I ground this terminal. I will make this ground this terminal. We can write the various potential differences, right? Different potentials with respect to B, which is being grounded. This terminal is at plus 12 volt, and A is at VTH. A is at VTH, the other terminal is at plus 12 volt. So we are able to identify 3 terminals or 3 nodes, 3 out of which one I have grounded. This is being 0, the other one is at 12, and there's a third one which is at VTH. Now we will try to apply simple KCL, and then we'll try to find out what is this VTH. Okay, if we apply KCL, we can easily see that the current through 8 ohms is called IX. IX can be written as 12 minus VTH divided by 8. This is the current IX. Okay, it is a simple fundamentals that we can say that IX current is 12 minus VTH divided by 8. The potential difference between the two terminals, that is one is at 12, another is at VTH. This is A is at VTH. 12 minus VTH is the potential difference across 8 divided by 8 is the resistance, that will give the current IX. Now if I write KCL at this junction A, what do I write KCL to be equal to? Also we have, if I can write the KCL equation, I can write simply IX is the incoming current. This is equal to the 2 outgoing currents. What are the 2 outgoing currents? 0.5 IX plus the other current is VTH divided by 29. Okay, it is as simple as that. So I will transfer, I am supposed to find out what is VTH, and I will replace for IX. So on this side, if it goes, 1 minus 0.5 is again 0.5 IX equal to VTH divided by 29. This is the equation I have. Okay, so now I will substitute for the IX. So I will get this to be, I'll have it as half. This is 12 minus VTH divided by 8 equal to VTH divided by 29. Okay, if I can simplify this equation, what will I get? This is to be equal to, I will write this as half into 12 by 8. I'm just expanding, and this is also equal to, on this side I have VTH by 29. The other VTH term I'm transferring onto this side. This is VTH by 16. Okay, so I'm getting this much. This, if I can simplify, this will come to VTH equal to, if I can simplify this, I will get VTH to be equal to 7.73 volt. This is a simple algebraic equation which I can simplify. Okay, so we are able to find the Thevenin's equivalent voltage, VTH, also known as the open circuit voltage. This is the open circuit voltage, right? So we opened this terminals A and B. We are able to see what is the voltage that is appearing across the terminals A and B. Okay, now the question is how to find the resistance. Okay, the Thevenin's resistance, RTH. How do we find this RTH is the question. Okay, so if we can look at this Thevenin's equivalent network, RTH comes in series. So in order to find RTH, we have methods. Suppose we have a network with only independent sources. What do? Is we try to replace the voltage source by a short circuit. We replace the current source by an open circuit, or in other words, we deactivate the sources. We're going to turn off the sources. Turning off of the source means no output is available. So that means across the voltage source, we don't get the voltage, and through the terminals of the current source, we don't get the current. That is when we say that the sources are turned off. Okay, sources are turned off. That means voltage should be 0 for a voltage source, current should be 0 for a current source. That is possible when you measure the voltage across a short circuit. Hence, a voltage source is replaced by a short and a current source is replaced by an open. But however, in this network, we have a dependent source. This is going to pose problems. You cannot simply, replace this current source by an open circuit. You can't do that because this is a dependent source. So in order to evaluate the resistance, the method that is adopted is very, very simple. It is very logical and very convincing. What we tend to do is we try to find out the short circuit current here in this network. If I can show that I short this terminal, okay, these two terminals. Suppose this is my ISC. Then we can write an equation for VOC, ISC and RTH, right? An Ohm's law equation relating these two quantities. So what I mean is we can simply say that the Thevenins resistance or RTH is given by VTH divided by ISC. It's acceptable. Voltage divided by current is the resistance for this network. Okay, and we know that this Thevenin's network, this network is an equivalent of this network, representation of this network. So it is as good as calculating this short circuit current here and dividing the open circuit voltage divided by short circuit current, I'll get RTH. That is the technique adopted. Okay, the technique adopted is we need to find out the short circuit current and we try to divide open circuit voltage by short circuit current to get RTH. Okay, so the next step is now to find out step 2. I will write step 2. What is my step 2? I am trying to get short circuit current. Not because I require a Norton source here. Of course, in this problem, we have Norton source also. So we need to find out short circuit current anyway. But however, in the absence of this Norton source also, we would have found I short circuit between A and B. Okay, the step 2 would involve in to find the short circuit current. The short circuit current. Okay, so I will take the circuit again. Instead of redrawing, I would prefer to copy the diagram. I'll copy this diagram. I'll take it here. Okay, now what I'll do is I will try to short the terminals A and B. So I use a bright color because short circuit is pretty dangerous. So I would draw a line. I try it like this. Now I'm shorting the two terminals A and B. Okay, so what is the current that would flow now in the path is I short circuit. This is the current. So we have to remember here this current, this short circuit path is being placed across this 29 ohm resistance. Okay, sources are on this side. You have 29 ohms and you have a short circuit. So will the current that would come into the junction, will it pass through 29? Obviously no, because this path is offering 29 ohms, whereas this path is offering 0 ohms. So whatever current that gets into the terminal would bypass this 29 ohm. The current will not flow through this 29 ohm because you placed a short across 29 ohm. So it is as good as this 29 ohm not being there. We can conveniently remove this. It is as good as having an open circuit like this. So this is going to be the situation now. Okay, if this is a situation, what is going to be the short circuit current? So we can simply say from this network, this is a very elementary network. What is a short circuit current? We can apply again KCL. KCL says I short circuit, the current that would flow out of this node A is plus 0.5 Ix. This is also the current that leaves the node A. ISC plus 0.5x should be equal to Ix. Simple KCL. What we have done is KCL at node A. Okay, applying KCL at node A, we are able to see that ISC plus 0.5x is Ix. Or in other words, the short circuit current that would flow is equal to 0.5 times Ix. Alright? 1 minus half is half Ix. Now what is this Ix equal to? It is the potential difference of this and this divided by 8 ohms. Right? So this, if you can imagine this end to be a ground potential, is at ground potential. So we can easily say that Ix equal to 12 ohm resistance divided by 8 ohms. 12 volts divided by 8 ohms. Okay, it is simply 12 divided by 8. Okay, that is what is the current to be equal to. This is equal to, what did I do? Yeah, this is what is Ix. Okay, so half of Ix, right? So it is 12 by 16. This is Ix. This is all right. This is all right. Now, ISC, the short circuit current, is equal to 12 divided by 16. Okay, how much will this be equal to? This will be equal to, I need to take my calculator and then let me quickly see what is the value of this. This is 0.75. Yeah, I could have done 4 3s or 4 4s or 3 by 4. Okay, 0.75 ampere. This is the short circuit current. All right. So we know the short circuit current. This is your Norton's current, by the way. The short circuit current, ISC, is nothing but the Norton's current. The magnitude of Norton's source, current source, 0.75 amperes. This is another important result which we would be requiring to write the Norton source. Okay. So now, having done this much, we will now find out the third step. What is the third step? Step number 3. Step number 3 is now to find out or to find RTH, the Thevenin's equivalent resistance, which is also the Norton's equivalent resistance. Okay, so we will try to find out this. How do we do? This RTH, which is equal to Rn, is given by simply VOC divided by ISC. Okay, so VOC is found to be 7.73 divided by ISC is 0.75. That will come out to be equal to 10.33 ohms. This is the Norton's and Thevenin's equivalent resistance. See, this equation can be understood either with Thevenin source or with Norton source. So let us look at the Norton source. What is Norton source equal to? If I look at the Norton source, the voltage that is developed here, this is the open circuit voltage. The voltage that is developed is IN into RN. Right? The current, the short circuit current into the resistance. That is the open circuit voltage. So open circuit voltage divided by the short circuit current is RN and RTH. So you can appreciate this expression either with Thevenin source or with Norton source. So having done this much, now we will write the Thevenin's equivalent network and Norton's equivalent network. Therefore, the Thevenin's equivalent network Thevenins equivalent network is equivalent network, and Norton's equivalent network, let me put in one sentence. Norton's equivalent network respectively are as below, as in figure 1 and figure 2. Okay, so in one sentence I wanted to cover both the things. All right, so now we will write the network. It is now simple. We will write a circle, a resistance in series. This is my Thevenin's network. This is my figure 1. What I have here is VTH, which is 7.73 volt, and this is RTH, which is equal to 10.33 ohms. And the second figure I will write is the Norton's network. So I'll write a circle. I'll put an arrowhead within it. Now I'll put the resistance. Sorry there. Where do I have to put the resistance? The resistance has to be across, right? It's a current source after all. I'll pick up colors. I'll take color A, B. This is Norton's resistance, whose value is 10.33 ohms. This is IN, the Norton's current source value. This is 0.75 ampere. And this is my figure 2. This is my figure 2. Okay, so figure 1 and figure 2 respectively represent the Thevenins and Nortons sources, just to make it colorful. Okay, this is my RTH, 10.33 ohms. This is my terminal A, terminal B. This is plus minus. This is VTH. What is the value of VTH? VTH is 7.73 volts. So this is my figure 1. So figure 1 is my Thevenin's equivalent and figure 2 is my Norton's equivalent. All right. Is this explanation, I suppose, is clear? This explanation should be all right. So we have done this problem wherein we are dealing with a dependent source. So whenever we have a dependent source, RTH or RN is calculated by VOC divided by ISC. That is all is new to this. Otherwise, the problem is simple. We can always find out the various things by simple KCL, KVL. Nothing extraordinary about it. This completes the problem. I think this is clear. So I've not done many problems on Norton's equivalent because the technique is simple. Thevenin's equivalent and Norton's equivalent are more or less the same thing. Instead of open circuit voltage, we find the short circuit current. And of course, finding out the resistance is simple. It is in the same manner. Okay. Thanks for watching. See you in the next video.